Begin by thanking Herman and Mark for inviting me, and especially Mark for beautiful work which partly inspired the work that I'm going to describe. Let me begin with the summary, the take-home message. I'm going to present evidence that, contrary to what we believe in, to Mark's beautiful work, there is mounting evidence that nuclear decays are, in fact, not random, that they're being driven by some external source, probably the sun, and possibly due to neutrinos. This collaboration involves a whole bunch of my students and now Peter Sturrock at Stanford. So the outline is this. I'm going to begin by describing why we got involved in this based on two data sets from Brookhaven and PTB in Germany, and describe an experiment we did which showed some correlation between a solar storm and decay rates. I'm going to focus on these two lines shown in red. There's absolutely no doubt whatever that there are periodic fluctuations seen in large numbers of data sets. The question is this interesting? There are two views. One is that, no, it's not interesting because what you're seeing is the fact that there are annual fluctuations because it's colder in the winter and warmer in the summer and your apparatus is responding. The second alternative is this really is not the case. And there are two arguments which are new and I'm going to present over here. One is we've done a detailed, very detailed Monte Carlo analysis of all the experiments and shown that any summer-winter-like effects are much too small to explain the data. But the much more compelling argument is that even though we see periodic effects in the seasonal temperature and so on, and in our data, the data show uniquely other kinds of periodicities, like 30-day periodicities, 154-day periodicities, which do not show up in the weather, which are uniquely associated to previously known periodicities coming from the sun. And this directly correlates our data to something coming from the sun. And to put it in this way, why would there be any frequency whatever in what is supposed to be random data that correlate exactly with things that have been previously known in the sun? And that is a compelling argument, and certainly not conclusive, that we are really seeing a new effect. Somehow or other, the sun in its various modes is showing up in the periodic data. I hear a bunch of references, which I'll just go through. This is the first paper on the correlations between decay rates and Earth-sun distance. At the same time, a paper on a serendipitous observation we made during the solar flare of 2006, December 13. I'll describe that. There's a review of this in Space Science Reviews. And this more recent paper, which is about ready to come out, is this exhaustive analysis of how apparatus really work in the presence of temperature variations. So how did I get into this? Completely by accident. First of all, if we go back to the days of nuclear decays, this is the classic work of Rutherford, Chadwick, and Ellis. It was originally published in 1930, and let's look at the history. In the early days, starting from scratch, this is an experiment done in 1907, I believe, just to show you what the thematic thinking was in those days. It was fundamentally a question, are nuclear decay rates insensitive to background effects? I love this experiment because it's the kind that Mark and I would have liked to think about. They put some radon, what we now call radon, in a strong metal container. They put in cordite, which is a high-energy explosive, and they exploded it. And the pressure went up to 1,000 atmospheres. The temperature went up to 2,500 degrees. And no, there was no evidence of any change in the decay rate. And that's the kind of experiments these guys were doing. And although you can't see it over here, and I won't bother quoting it, basically at the top over here they say, talking about decay rates, it is unaltered by exposing to anything. The rate of transformation of an element has been found to be constant under all conditions. That is the paradigm that started with these guys, which we now believe to be correct. So how did we get interested in this? Quite by accident, I was working on some other problem motivated by some insight from my colleague Al Overhauser, who's the O in the COW effect. And out of this came a new test of randomness based on geometric probability ideas, which I won't go into. But after applying this to the digits of pi, we decided to do an experiment. Just the kinds of things that Mark was doing, but with a homegrown test that we had just published. And I convinced my colleague, Dave Elmwood, to do this experiment at Purdue. And the most serendipitous of all events in this talk is that it gave me one of the only two papers I've ever seen which would have been the motivation for this. Somebody had measured the half-life of silicon-32. You can see at the outset that there's already a problem, even in the abstract. Their result, 172 plus or minus 4 years, was in way disagreement with two results obtained by different methods at the same time. And this, in fact, is a common theme in these things not to be discussed not often discussed. There are a huge number of discrepancies of this sort in the literature. But that's not the source, that's not the real part of the story. In order to understand how these experiments are done, and this is critical, you have to understand what the apparatus looks like. This is their apparatus, and we own it now. They've been gracious to give it to us, Olberg et al. You have two samples, let's say silicon over here with a half-life of 172 years, and behind this, on another micrometer, long-lived standard, which is in this case chlorine-36, having a half-life of 301,000 years. The experiment is like this. There's a detector which has been removed over here. One apparatus, one sample sits under it for a half hour, then you move back and forth and back and forth, and this cancels out any systematic effects. The idea being chlorine tells you what's really going on, and you cancel any fluctuations in this way. All right, as soon as you read this paper, and as soon as I looked at this, there's already a problem. Chlorine, which is very long half-life, over a period of 4 years, should be seeing statistical fluctuations, but even by eye, you can see that there are roughly annual fluctuations. And if you detrend the silicon data, you see exactly the same thing. If you take the ratio, which is supposed to eliminate all fluctuations, you can see, in fact, there are still fluctuations, and that is not supposed to happen. And if you detrend the data and get rid of the actually known half-life, you see there are clear fluctuations. Here, the 4 years of data of this experiment are overlapped on top of one another. This is their paper. And as it says in the legend here, a clear annual effect is evident, and we agree with this. We have the data with the minimum maximum February and August. So there's clearly something wrong, and our objective was to do an experiment of the sort Mark was doing, but we had to understand what was going on here before we got too far ahead. And they concluded after doing their analysis that there's clearly a systematic variation, but they looked for experiments for effects of temperature and whatever, and they could not explain their data with those effects. Now, we asked the following question. If this is a real effect, then probably some other experiment has seen it. Now, I went through clearly several hundred papers, reading and skimming them, and there are very few papers, oddly enough, which would even have thought about doing the experiment in this way. But one of them was this incredible experiment at the PTB in Germany by Heinrich Schrader and his colleagues. And it was...
Can I stop you just a minute and ask
you,
why is it that the Brookhaven group were looking at the decay of silicon-30?
It has, because silicon is, for cosmogenic reasons, because silicon is a constituent of rocks and so on, for dating rocks and cosmic fluxes and stuff like that. So it needed that half-life. And it's very hard to determine, and it would only been poorly determined for those reasons, yeah. Here are their data as published, and without any statistical fancy analysis, you don't have to be a rocket scientist to see there's an annual fluctuation here. Here are 10 years of data, and there's obviously something going on. These are now data on the decay of radium, which has been detrended, but radium has a half-life of 1,600 years. Now, we're going to come back to those two data sets, but these experiments motivated us to do our own experiments, and we were studying manganese-54. And here already you see yet another problem. The problem is the green line is the published expected trend line, but somewhere in the middle of this, and we see this in the PTB data as well, the normal trend line, which corresponds to a half-life of 313, our data said 313 days. The published value is 312 days. That's not relevant here. But there comes a time for a few days when you get what we call these flat regions. You get the same number of counts hour after hour, day after day, even though the sample you have is decreasing in its population. How is that going to happen? The actual half-life corresponding to that is about 6 times longer during this region than the nominal value, and that has medical implications. And this is being studied by people at Mayo Clinic, one of our collaborators, because if it is in fact the case that sometimes you're giving people more or less radiation than you think for whatever reason, obviously people are going to be affected by that. Now, here's the data from our group in December of 2006. Again, our data more or less following the trend line, but wait. I love this part of the story. In December 12th in Indiana, December 13th Universal Time, there was a major solar storm. What happened was when this storm occurred, there was a mission to the International Space Station. And at that moment, when the storm actually happened, the astronauts were outside the space station, were hit by the solar storm. Now, it was a low level called S2 level storm, but if it had been an S3 or S4, they could have been killed. So this raises one of these questions about what we can do with space travel. But in any case, it caught the public attention, and we saw this and went back to our data. That storm came from a spot called 930 on the sun, and as the story unfolds, that spot rotates from your left to your right as the sun rotates through its 30-day period. Here's another picture of that spot. Here are now the data that we collected. Here's a trend line that I showed before, but here it is, exactly coincident with this flare. We saw our data leaving the trend line, and there's roughly a 7 sigma effect. The data returned to the trend line afterwards, as you'll see momentarily. Here is again the timing of that event. And notice what's absolutely critical over here, both in understanding what may be going on and in understanding an application of this. Because what we see is that literally this solar storm is a burst, an explosion, which happens without warning and lasts about 40 minutes or so. But you see in our data, there's a precursor signal over here of about a day and a half. So if this is reproducible, and it appears that it is, it lends the possibility now that we can forewarn NASA and astronauts if we understand what's going on. And it appears to be that this is, in fact, a real possibility. And here's again the same picture. Notice there's a precursor signal. And again, over here, you can see our data eventually returned to the trend line when the storm goes away. Now, here's another picture of the same data. Let's start over here. Here's a major solar storm, but that occurs when that spot is...
Can I ask a question? The
Sure.
solar storm, we showed a picture that moves over the surface. I know nothing about solar storms. How long does it take to do this? Is this divisible during a full rotation? Is there shadow in the sun?
Good question. That spot is bolted to the sun. The sun rotates at a period of about 30 days. That spot will move across at about 30 days, but that spot, when it erupts, just erupts from that spot and lasts 43 minutes for this one spot. So you have a spot, and then boom, it explodes and goes on. And yeah, so here it is. It starts on the left side, you have boom, an explosion, the sun rotates some more, boom, another explosion, and that's it. That's the picture you want to look at.
It means that during that time, the Earth is rotating.
No, I like the sun, but that would also be a good question.
No. I was going to say the same thing, Sam, but you just took my line away. Okay.
Oh, I'm sorry.
Notice what Sam really wanted to say, because he's very smart, is that if you look at this, in this 1.7 day period, the Earth is rotating, and yet the signal doesn't seem to care about the fact the Earth is rotating. The signal is going through the Earth or not through the Earth, and that's the hint that we're about ready to come to. This may be due to neutrinos, which are the one mechanism you'll see which can explain all these data. You see over here, so here's that spike that we're talking about. This is a big spike, but again, the energy was directed away from the Earth. Here's a typical error bar. Let's look at some more versions of the same thing. Here on a logarithmic scale, you see the same picture. Here's a spike we're talking about on December, 13 Universal Time. Here's that we'll call it Sam's delay. Here's another solar spike, again, another dip in our data. Here you see that solar spike and a dip in the data, and Sam, you've been immortalized, okay? Now, at this point over here, that spot rotates out of view. And now, to answer your question, that's in the back of the sun. We don't see any radiation. We still see events over here, yet another signal that we're getting information from the unseeable part of the sun due possibly to neutrinos. Now you see the whole month of December 2008. Here are the spikes. Here's the spike of December 12th in Indiana time. Again, another spike, another dip in our data. You see, at this point, the sun rotates out of view, but nonetheless, we see events over here. Eventually, return to the trend line, okay? So we see strong correlations between our data and, as you'll see in a few minutes, the argument now leads strongly to neutrinos. We'll explain. I said before to Herman's question, here's a December 6th flare. You see, it's just beyond, on the other side of the horizon. So most of that energy is going that way instead of to us. And so we see less of a signal. Here's what that spot looked like in several pictures. I'm not animating it to save time. Now, fortunately for us, yet another serendipitous event was that this occurred in December 12th, Indiana time. And we were like 4.5 hours into nightfall. So whatever, the picture is this, whatever hit our laboratory over here in Indiana traveled through the Earth, and we reconstructed its path. It landed at Butaratari in the Pacific, for those of you interested in geography, traveled about 9,200 kilometers through the Earth, and arrived simultaneously with that solar flare. So the question is, what is it that what signal could the sun send out that would travel through the Earth at essentially the speed of light and arrive coincident with X-rays? Well, one candidate is solar flares. And then, of course, because the Earth is rotating and it doesn't seem to care what's going on, again, gives us a picture of possibly neutrinos. So the picture we have in mind is that there's some cauldron boiling underneath the sun. Whatever it is doing is producing neutrinos, which do get out and which give us the precursor signal, but the radiation, the electromagnetic radiation, is yet to come. Now, having seen this, we went back to our data in November, and here again we saw the same thing. Here is a significant storm, and again, you see associated with a bunch of dips in our data. So it seems to be a repetitive pattern. I love this slide. When we published this paper, I love them all, but this one in particular. When we published this paper, the referee said, okay, you've seen correlation with your data in a period when the sun was active, which is December of 2006. What does it look like when a period and when the sun was quiescent, which the sun has pretty much been ever since 2006. So we showed the referee this slide. In fact, the data are very quiet, as you expect. So when the sun is quiet, our data are quiet. When the sun is noisy, our data are noisy. But to the trained eye, we also noted, if you look right here in that center, there's a little hiccup in the data. So just for fun, we said, OK, let's play around and see what happened on that day, which is December 16 of 2008. We just arbitrarily picked this month. Here are what the data look like on a slightly blown up scale. You can see it's leaving the trend line over here. And sure enough, when we looked at the data, there it was. There was something on the far side of the sun actually caused a solar storm, a minor solar storm. Here's a picture of it. So exactly coincident with our data, there's yet another event, which we didn't expect, but we looked at it, and sure enough, it's there.
The signal went up.
What?
The signal went up in this case instead of down.
Yeah.
That's okay, because we don't really know what's coming out of the sun. We do not understand the mechanism, and that's fine. That's a perfectly legitimate question. Let's come back to that at the end. That's exactly right. Now, here's another picture of the same data. Notice again that the line, this sort of horizontal feature where the data leave the trend line. But again, something is coincident with the flare. And notice again how much the half-life changes during this period. These are not small effects. Now, neutrinos, can we talk about neutrinos? Well, we know from Super Kamiokande data, where we really do know we're seeing neutrinos, that neutrinos are in fact coming out of the sun. Here's a plot of 1 over r squared, distance between the Earth and the sun. And roughly we see a correlation that when the Earth is closer to the sun, we get more neutrinos. The data are poor at Super Kamiokande because the event rate is only about 15 events a day, but clearly there's a trend. So this is raising the question of neutrinos. So let's go back now to the Brookhaven data and the PTB data, which we saw before. We asked for and received the Brookhaven data, and we detrended the data. We've all been doing this. So this is taking out the nominal half-life. The red curve is, again, 1 over r squared. You see, again, clear correlation between troughs and peaks, but with a phase shift of about 30-some-odd days. That phase shift is important because all the data see the same phase shift, and there's real physics in that. If you clean up the data and do a 7-point rolling average, there's clearly an annual period. There's clearly also a phase shift, but the fact that there's a periodic effect is now perfectly convincing. Here are now the PTB data. We have more data than they actually published. They gave us the whole data set. They're like 15, 16 years over here. And superimposed on this is, again, 1 over r squared. Very clear correlation between Earth-Sun distance and peaks and troughs in their data. And if you clean up their data, you see the effect even more clearly. Interestingly, you also see these kinds of events over here, which seem to be perhaps representative of peaks in the solar cycle, the 11-year solar cycle, but we can talk about that later. Now, the third serendipitous event was that these two experiments were running at the same time. PTB ran for 15 years, Brookhaven ran for 4 years, but 2 of those years overlapped. So if this is a real effect, we can ask, do these two data sets look like? And we're not doing Mark kind of correlation. We're doing sort of kindergarten level. We're doing it more sophisticated, but here it is. Red curve is 1 over r squared. The blue curve is Brookhaven. The green curve is PTB. You see these curves very clearly have the same, roughly the same peaks and troughs. If you clean that up a little bit, you see again the blue from Brookhaven, the green from PTB look very similar. And again, they both have phase shifts. Now, if you look very carefully, you'll see the phase shifts are not quite the same, but there's a reason for this. And if there's a question at the end, I can explain why, or at least give you a theory why this works. And here the same data are now the 7-point rolling average. There's clearly a periodic effect. The experiments clearly are seeing something which looks the same. And I emphasize these two experimental groups have no idea of each other, since I know all of them, and certainly no idea of each other's experiments. Nonetheless, they're seeing more or less the same things. So once this stuff got published, a number of stories came out, and Nature, Physics, Science News, and so on, and people started sending us data sets. Here is a data set from a guy named Ellis, who is doing, he's doing in vivo neutron activation. They put people, I'll show you the apparatus, I guess. First let me read the last line of this thing. induced counts on a manganese standard on a yearly basis indicate that seasonal differences of approximately 0.5% can be present between winter and summer. It's exactly the same effect we've seen. Now, this guy isn't going out to measure anything, not to do a NIST-type measurement, but he's noticed this in his data. This is sort of a 1950s horror picture. You're a patient, you're stuck in here, you're radiated with neutrons. They want to know how your bones are growing. And so but they have to calibrate the flux with something, and all these data come from the flux. The process is, you know, a pubic source produces neutrons, produces this, produces that. Eventually, you get a decay of iron into a photon, and that's what's counted. And I'll skip this picture. Here, we got the data from this guy, Ellis. And again, you see, even though he's not going out of his way to do this, troughs and peaks coinciding here. He's, of course, not as precise as PTB or whatever, but clearly there's an effect. And when you analyze this in details, I'll show you in a minute, he's seeing the same periodicity, the same phase shift that everybody else is seeing. Now, this guy, Ellis, thought this result was so crazy, I've spoken to him, that he thought of not publishing it. So it's clear he worried about this, and in his paper, he's done a lot of tests to see that it's not a seasonal effect. It's not due to temperature. He wanted to understand why his patients were seeing funny kinds of fluxes. So it's quite clear from his analysis he's worried about a lot of these effects, and that's part of what forms his background. Now, data from other institutions. Again, somebody's mother-in-law read about our story and told her son who worked at the Ohio State, thank God for mothers-in-law, and told this guy, these people work at the Ohio State reactor. Every week, by law, they have to do swipe tests for contamination, and they calibrate their apparatus again with the same chlorine 36. Same chlorine 36, and you see again clear periodicity. The dots are the actual data. The blue line is just a fit to those data. You see peaks and troughs coinciding. In fact, when you do this carefully, they're seeing more or less the same period and periodicity and phase shift as in the other data. Here's a paper that just came in the last week or so from Parkhomov in Russia, who's been working on this even before we were. Again, you see in this case, these are data on strontium and yttrium. Here's the data on cobalt-60. You see clearly periodic effects as well. More or less, his verbal description is the same thing we are seeing. Interestingly, he does not see anything in a pure alpha decay. These are all beta decays of one sort, which is in agreement with the results that we and others have obtained. So it seems to be more or less focused on alpha decays.
But that stuff looked like it was annual.
Yeah, and that's it. He's seeing an annual period. We have not yet analyzed his signal for sub-annual periodicities. We just got this paper. And Parker was in the process of sending this. Now, if you look at everything, you see there are actually a whole bunch of, we made a big deal out of two experiments, PTB and BNL, but in fact, there are a lot of these experiments now. This is Ellis's data is Ohio State. This is Parkhomov. Different detectors, different apparatuses, annual signals, and our flare data as well. So it seems to be sort of a more widespread phenomenon than one would have thought. So let's now go back to this question of phases. The idea that data should correlate with 1 over r squared is the idea of a picture of the sun, which is a uniform ball, and we're just measuring our distance from it and so on. But in fact, the sun is believed to have internal motions and so on. And if you correct for what's called the heliolatitude effect, this is a contribution from Peter Stark. That is to say, there's a north-south asymmetry of whatever it is in the sun, plus the fact that it's Earth is getting closer and farther away. You can make you can fit it. I don't want to say there's a prediction. You can fit it to this phase shift, and everything works out. So it looks like, according to Peter Stark, you're seeing more fine structure in our data, which would be indicative of more complicated dynamics inside the sun. And if you fit the same model to PTB, the data sit just on top of it. Well, it's partly the result of a fit. Partly the answer to some of these questions is that the PTB folks took data on different samples, and here's an example of a sample. This is europium-152, where it's out of phase. That is, where you have different samples, some of which increase and some of which decrease during the year. So it is not clear that an increase in flux uniformly causes an increase in decay rate. That is, it's not clear that being close to the sun makes all isotopes, first of all, change in any way. Second of all, they don't go in the same direction. That's their own PTB data. So the picture is more complicated, but nonetheless, they see a periodic effect, and they've commented this long before we got into the business. Now, we can go back and do now more refined analysis of what's going on. First of all, for these data, for Brookhaven. This is Ellis's data, PTB in Ohio State. At least for this data set, everybody does in fact see, not just by eye, but analytically, roughly 1-year periodicity. But they also see low frequency things, and I think you were talking about this. That is, if you're seeing part of an 11-year cycle, it would look like a trend, and that appears to be what we're seeing over here as well in the decay data, which is also very reassuring. Now, in this whole talk, there are a lot of slides that are my favorites, but this is my favorite of the favorites. I'm going to try to explain this, take a few minutes to do this. This is an analysis from Peter Stark, our colleague at Stanford, who's an expert in these things. It's called a cum sum analysis. Let's suppose on this right curve over here, CL are the Brookhaven chlorine data. If you were just seeing noise and you looked in the different frequency bands, let's say the first band has a power P, the second band has a power P, but the first 2 bands would be 2P, the 3 bands would be 3P, and so on. So you'd see a line that's roughly, that's this line, sort of a sloping line in that direction. What you actually see in the Brookhaven data is that this line has a break at around 10 per year, between 10 and 15, so an average of 12 per year, or 1 a month, a frequency associated with the rotation of the sun. Shown in green on the same slide are data from ACRIM, which is a satellite measuring the total electromagnetic radiation coming out of the sun. So this is a surrogate for all energy production from the sun, from neutrinos and everything else. And remarkably, at least to all of us, these 2 curves sit right on top of each other. You have to ask yourself, by what means would a set of experimental data measuring radioactive half-lives show periodicities? We're not seasonal effects now. Periodicities that exactly track periodicities that are known and have been known for a long time to be uniquely associated with the sun. By contrast, on this curve over here, this is the same chlorine data, but this is a profile of the temperature, the frequencies you see in the temperature distribution at Brookhaven. And you see nothing, roughly speaking, aside from noise. These 2 don't look like anything. They certainly don't look like anything in this period where you see this sharp break in frequency. So what you see from this slide and the next one is that there appear to be periodicities in the data which you would have no explanation for other than the fact that they look like the sun because they're being influenced by something, whatever it is, coming out of the sun. The same thing now on this slide. This is now this is the power. Well, you've talked about that. This is the power of a given frequency as a function of frequency. Here it is in this band of roughly around 12, which is 1 a month, which is roughly the rotation rate of the average rotation rate figure of the sun. Well, the sun has different rotation frequencies because it's not homogeneous. So you see in this band over here how closely the electromagnetic radiation from the sun as a function of frequency tracks the experimental data out to here. This point is already, this is a sort of a harmonic of that peak. So beyond here, the fact they don't agree isn't physically significant. So it's another remarkable way of looking at the data. Bottom line, the sun exhibits certain frequencies which have whatever they do for whatever reason, but our data on these Brookhaven, these little samples over here are showing exactly the same periodicities. There should be no periodicities. We're seeing 1-year period, we're seeing 1 a month period, we're seeing, and on top of everything, which we don't have a slide here, we've just discovered a 154-day period in our data. We don't have a slide on that. That's a period that's called a Rieger frequency in the sun. It has to do with oscillations of a rotating fluid, which we won't go into. Now, let's go to possible mechanisms. How much time do I have?
You have 10 minutes.
Okay. There are basically well, there are lots of mechanisms. Let's try to think about what they could be. One mechanism is to follow the current discussion on time and spatial variation of fundamental constants. So imagine the fine structure constant varied, and there was some field which caused that to happen. If the fine structure constant varied, then it would certainly affect both the alpha and beta decays. That could be a mechanism. Let's just do this briefly. You can ask, well, how would you explain the data in a simple model if the fine structure constant alpha varied? And it would take a variation. Actually, the effect is pretty big. It's like 0.5%, as Mark was talking about. That number is way too large to agree with various atomic physics experiments, some of which I've heard in here many years ago. So that is probably not the mechanism that explains this, unless you have a more sophisticated model where both the fine structure constant and, let's say, the electron to proton mass ratio varied in some way. So let's skip that and go to the second mechanism. This is what we think is maybe really going on. Here's a schematic of, let's say, neutron beta decay, either as a free neutron or as a neutron in a nucleus decaying. The picture is at the solar a solar neutrino, nu S, comes along and exchanges an amount of energy delta, let's say with the emitted neutrino, or possibly with the emitted electron or the emitted proton, and changes in some way the phase space of the final state particles. Now, we all know that beta decays are extraordinarily sensitive to phase space considerations, which is part of the explanation why half-lives of beta decays extend from fractions of a second to tens of billions of years. This is one of the mechanisms. And if you want to convince yourself of this, you can think about the difference in half-life between a free neutron, which is about 886 seconds, and tritium, which is like 12.36 years. That difference, which is a factor of 10 to the fifth or sixth, occurs because the energy available differs only by a factor of 2 or something like that. So small energy differences produce huge effects, and so it's reasonable to assume that a small kick of energy from a solar neutrino just passing by could perhaps modulate the decay rate or the half-life by 0.5%, which is not a lot. Now, we had this discussion of delta squared, and now Sim's going to understand why I worried about this. One mechanism of this, one consequence of this, I won't go into all details of the model, is that the neutrino for a polarized sample would sort of contribute to this term in a spin-spin interaction. But if the sample were unpolarized, the net effect of this would be you simply end up with a simple quadratic term delta squared. It would kick the energy in this way, and that would change the half-life in the manner that's indicated. Now, what is really cute about this, of course, you cross our fingers that this is right, is that we didn't set out to make the following observation, but it turns out to be neat. If you take current tritium data, and tritium is used to measure the mass of the neutrino by measuring the endpoint energy, if you take the current data and fit it to neutrino mass squared, the answer is, in the particle data group, is that almost all values of the neutrino mass squared are negative values. The top line, probably written by a bunch of lawyers, given troubling systematics which result in improbably negative estimates of m nu squared. That's simple English for the fact that all these experiments are giving a negative value of m nu squared, including their average. It's an embarrassment, and it's been around for a long time. As you can see from these data, these things go back to 1991, and I was at the early conferences at Montreal where this came out. Well,
fitting that to a full Gaussian, they should be fitting it to probably a half Gaussian.
Well, no, they do something simpler. They just give the data to a computer and say, here's the formula, tell me what m nu squared is. Well, the computer doesn't know that it's giving you an embarrassing result. So it says, if these are the data you're giving me, I'm giving you a negative value of m nu squared. So let's go back. Now, it turns out, however, that if you take the data and say, no, m nu squared is so small that it's below your level of detection. But what really is going on is this mechanism that we talked about, the one that I described over here. Then it turns out that for kinematic reasons, delta squared, the delta squared turns out to be minus 1/2 m nu squared. So that is to say, if the mechanism is really what we're talking about, the mechanism that would explain all these periodic variations, it has as an accidental consequence that it would look like you're looking at a theory with a negative value of m nu squared, even though that's not what's actually going on. This could be an explanation of why people are continuing to see m nu squared. That's just a thought, and we'll leave it at that for the moment. And the value would be something in the range of 50 to 5 eV squared. And here are the negative values of all these folks. Now, if this has to do with neutrinos, you may say, how much time do you have now?
6 minutes.
Good. If this has to do with neutrinos, you say, look, why don't we just take our apparatus and stick in front of a reactor somewhere and see, look for changes. So Jerry Jenkins and I did this in the beginning of, in January of 2007. We took it to the Penn State reactor, the Brazil reactor, where among other things you can pulse it. That is something to see. When you pulse this reactor, you get this incredible, like this little atomic bomb going off, which is just awesome to see. But in any case, we did the experiment. It turned out to be inconclusive because when you get close to the core, which is where you want to be to get a large flux, you also get a large flux of radiation, and we didn't have enough lead, even though we had hundreds of pounds of lead. So we planned to go back and do it. But in the meantime, we realized that there's a better way of doing it. The better way of doing it, and now you see Dick Lindstrom, our colleague in this, is we convinced Dick Lindstrom and Jeff Green, who's also on this team here, the following. Suppose you take a sphere, a little sphere of gold, and you irradiate it. Well, gold has a half-life of about 2.7 days. As the sample is decaying away, the neutrinos which are emitted by the atoms which have decayed bathe the remaining neutrinos, the remaining nuclei in neutrinos, just as if you were standing in front of a reactor, except it's a completely calculable effect. And the experiment consists of measuring the half-life of a sphere of gold compared to a foil of gold, where in the foil all the guys would escape without doing much. So this is largely the thesis of one of my students, John Buncher. It's a beautiful job on the math and the analysis. And the idea is this. So all samples are basically bathing in their own neutrinos. So what you have to do is irradiate the sample to the level where the sample is being bathed by more neutrinos that are already coming from the sun, which is sort of a random fluctuating background. And we figured out with Dick that you can actually do this. And as it says over here, for a sphere of gold 197, where you irradiate with neutrons to form 198, you can get a specific activity of 10 to the minus 4, and that does it for you. We're actually repeating the experiment with higher activity now. Dick is, when you get back to NIST, tell Dick that I want to know what's going on with the experiment. All right, here's what the physics looks like. This is the decay rate, except now lambda itself depends on time, because as the sample decays away, the contribution from the self-induced neutrinos, this term over here, gets smaller and smaller. In any case, this leads to a first-order but nonlinear differential equation. This has an exact solution, which I won't go into. So now let's talk about what the results look like. So the experiment asks for the ratio of the half-life in the foil and in the sphere, and the results were, good for us, inconclusive. Depending on which experiment, it's 0.9968 plus or minus 0007. That differs from 0 by a couple standard deviations. And in this run, we did actually 2 experiments. Dick did them, again, indicating a slight discrepancy. This is absolutely not to be taken as evidence that neutrinos do anything at this point. We don't understand the data, despite Dick's diligent efforts, which is why we're repeating the experiment now at a higher intensity and hopefully doing a better experiment at that. But this is a beautiful experiment because it's completely controllable. The radiation level, the activation level is controllable, the math is controllable, everything's controllable. It's like a beautiful mini experiment, and gold is the ideal sample to use. Now let's talk about environmental sensitivities. As I said at the beginning, and coming back to this at the end, we've modeled, these are all the numbers we use. We've modeled the Brookhaven and PTB experiments. Here's the Brookhaven experiment. Here's a picture of how we modeled the detectors. We actually have the apparatus. We have the sample, so we can measure everything. And knowing what we know about the experiment, we've modeled this using this program MCNPX, which is what's used, for example, at the Mayo Clinic to give you radiation doses. And our colleague Dan Mundy has done this work with Jerry primarily. Bottom line from all this, the effects you see are fractionally parts in 10 to the 5th per degree Fahrenheit. You're looking for effects that are sort of 0.5% or close to 1%. When you put all this together, we've done all the calculations of every possible effect, energy deposition here at the window with the source, every possible calculation you can do, and every possible number we've come out with says the effects are just too small for the Brookhaven data. At PTB, the big issue, the claimed issue of backgrounds, but we've talked about, calculated all the backgrounds from radon, this, that, and the other thing. Bottom line, again, is that for any known background and anything we could put into the calculation, the effects are just vastly too small. So now, this calculation says if you just do brute force and ask, can summer-winter effects actually explain the data, this calculation says no. But the previous results about periodicity say absolutely not, because whatever weather does, it doesn't have 30-day periodicities, it doesn't have 154-day periodicities, it doesn't have these other periodic effects which do come out of the sun and which have nothing to do with temperature, either in Braunschweig or Brookhaven and so on. All right, there are a few papers have been written criticizing us. I'll just do these briefly. Peter Cooper has talked about, these are the concluding remarks, about the fact that you can analyze data from the Cassini spacecraft, which has a plutonium source on it. The short answer is, first of all, those data are crude for various reasons, but the real reason is that this is a pure alpha decay. And so we are believing now that when you see something in radium, it's not because you're seeing the alpha decay of radium, but rather you're seeing the daughter products, the daughter, the granddaughter, the great-granddaughter, which involve things like lead-210 and so on, which are beta decays. So this is not a criticism of us, but it's an interesting observation, which we're following up on. There's a paper by Norman who's done a whole bunch of other isotopes claiming to see no effect. There's nothing that says that every isotope has to show this effect. It's almost for sure that some isotopes will not see this because of the same kinematics and dynamics we've spoken about before. But in fact, off the record, we'll say that part of our group at the Air Force Academy have reanalyzed this data, which we've been given by Norman graciously. And there is, in fact, an effect of the same phase shift as seen everywhere else. It's just at a smaller level than he was worrying about. This is a paper by Semko, which is basically a wrong criticism based on summer-winter effects. So here's a summary. Basically, starting out with Brookhaven and PTB, there are clearly 1/r squared dependent effects, suggesting that there is a sensitivity of the decays of whatever was in the radium experiment and chlorine and silicon at Brookhaven to the distance between the Earth and the Sun. The phase difference we think we can understand if the Sun has sort of a north-south asymmetry. On top of that, there's a data we took ourselves by accident, this flare of December 12th, which has nothing to do with seasonal effects, but which show again that when the Sun presumably changes its flux of neutrinos, our system seems to respond every time we're able to track it down. So this is a picture that the data being modulated in some way by something coming out of the Sun. Now we can eliminate, or we're on the verge of eliminating, environmental influences, temperature, and all that because of the analyses we did, the detailed analysis which I just described, and these phase issues which are really absolutely critical. The fact that you see periodicities which are completely unexplained and unexpected, but which closely track things which are previously known in the Sun, suggests that we are seeing something intrinsic to the Sun, and that's what's exciting us, and so on. We have more data coming in and more data being analyzed, but it seems to be that every data set we acquire says more or less the same thing. So these are rather common, I would say, sort of common effects, phenomena, and of course we end this with more experiments are necessary. I'll stop here. Thank you very much.
Questions? Let's first go with Helen.
You're speechless because you can't possibly believe this.
In these two last lectures, anyway, there was no comment, let's say, that there may be a Zeno effect, yes, in this decades, because in atoms we know that there is a Zeno effect, yes, when you have a decay and you have immediately, you observe the next one later on and so on, and when you observe in between the system, whatever, in whichever case,
oh, I understand, yeah.
then you get different decays, so you can influence the decay time, at least of an atom, by subsequent or successive measurements.
Okay, so I understand. But the answer to your question is that that's not the way these experiments are done. The PTB and BNL data were taken at monthly intervals typically. So you're not talking about repetitive signals of the xenotype, which would require doing measurements over a very short time. You're talking about accumulating data over a month at a time, or a day at a time, then a month at a time, and over a year at a time. If that's an interesting effect, we'd like to know it, but I don't see why those things would correspond to periodicity seen in the Sun. But it's an interesting idea. I don't see that would correspond to what was actually done, but it's worth thinking about.
Mark?
I noticed that in almost all the graph plots that you had showing the periodic variations, that the amplitude of the variation was about 0.1 to 0.2%. From the sort of work that we were doing for entirely different reasons, I know that we would not be able to see such an effect as if we were plotting the actual counts and the fluctuations to be such that if there were a modulation in there, or periodicity of 0.1 or 0.2%, we would not see it. So it seemed to me that the reason why the plots are so clear, and one doesn't need a statistical analysis, that you're plotting something different than we are. You're plotting a ratio to chlorine 35.
That's right. Yeah.
Is there anything that can come about of an explanation or a refutation of or interpretation by virtue of plotting a ratio? Is there something?
No, yeah, I understand. If first of all, the motivation again. If you're just seeing a fluctuation, let's say the line voltage or whatever, that would affect the detector, and you should see a constant. Since you're seeing them the samples are measured back and forth, that should cancel out. So the first thing you see is that the mere fact that the ratio itself shows a periodic effect pretty much indicates that you're not seeing just an effect of the detector. That's right. So you're not seeing background, you're not seeing any stuff like that. And that's common to all the experiments. That's common to PTV, it's common to, let's say, the Ellis data and so on. Ellis, again, even though he wasn't setting out to do this, he had cesium-137 and manganese-56 in his apparatus. He measured this over many, many years, always cesium, manganese, cesium, manganese. He sees no effect in cesium. He sees a clear effect in manganese. So one tends to think that it's probably not some kind of apparatus thing like that. That's our thinking at this point.
I would like to ask one question, maybe the last one given the time. In comparing again to atomic decay, right? We know about inhibition of spontaneous emission by changing, the modes in which a photon can decay by the presence of it. Now, is this mechanism to be understood that in beta decay there is some neutrino, and if you now present in the environment, you change the amount of neutrinos available, you are changing the exit channels for the neutrino? Is that what's going on?
That's what we think is going on. Yeah, it's a good point.
Would that then
Yeah.
also mean that since, I guess, neutrinos will come maybe, well, if you can control the modes in a certain way, right, then you might also affect the decay rate.
Well, we think the sun is controlling in some way and doing just that. So your picture is correct. We know that if you can find an atom in a box, you eliminate some of the modes, you change the decay rate. In a sense, you're changing the phase space here not by confining atoms in a box or nuclei in a box, but simply by pumping in energy from outside. You're doing more or less the same things. Whether it suppresses or enhances decay, we don't know, but it's pretty much your description of changing the available phase space, which is the way I would describe it, is correct. That's what we think is going on. Yeah.
Okay, then let's thank our speaker again.